The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's get down to business. One announcement. Tomorrow will be weekly quiz number 11 based on homework 11. And then, of course, Thursday and Friday there will be no academic exercises in connection with the Thanksgiving Day holiday. So, last day we started talking about polymers, macromolecules. These are chemicals that have a very high molecular weight with a repeating chemical structure. I've given an example here of vinyl chloride as the individual molecule, and by addition polymerization we can break that double bond, have it propagate, and we end up with something which is the polyvinyl chloride. N numbers can be very large, and we can get molecular weights in the vicinity of 1,000,000 grams per mole. We further looked at tailoring properties by control of molecular architecture. We saw that we could look at bulk composition and form such things as copolymers, which are to polymers what alloys are to metals. Another way of tailoring properties is to vary the arrangement of the side groups on the backbone. This is the tacticity of the polymer, and it is to a polymer what stereoisomerism is to individual molecules. And then lastly, we looked at the shape of the backbone itself, different conformations, and this is owing to the rotational capability of the carbon-carbon bond. And at the very end of the lecture, we looked at two forms of formation. One is addition polymerization, which is shown here. We have the three stages. We start with initiation. Here you see hydrogen peroxide, which is turned into the radical, and that triggers this reaction, which then moves the unpaired electron to the end here, and this is sticking out like a hot poker, and other gas molecules, in this case ethylene, that come in contact with it will in turn have their double bond broken, and so on and so on. And finally we get to the length that we want. We terminate the reaction, and that's the end of the process. The second one was condensation polymerization. And condensation polymerization is stepwise, where you take two different mer types, and here's a cartoon showing an example of the formation of PET. This is the material that's used for soda bottles and many of the clear plastic containers that you find in the supermarket or the drugstore. So this one vividly indicates that it in fact is an acid-base reaction. I said last day you had an R1, which is a proton donor, and an R2, which is a hydroxyl donor. Well, those are classical Arrhenius definitions. And so in this case you start with terephthalic acid, which is basically benzene with this carboxylic acid on the end. The COOH is carboxylic acid. We'll see that repeatedly. It's a basic group. Basic is the wrong term. It's a group intrinsic to proteins. It's an acidic group. It's not a basic group, but basic meaning a different way. Huh? So here's terephthalic acid. Here's ethylene glycol. This is what you put in your cooling system. This is the same thing as Prestone 2 antifreeze. It's a double alcohol. It's got hydroxyls at both ends, so it gives up one of those, combines with the proton here to form water, and then we form the amide bond, which then starts the polymer here, and it in fact is a polyester, because at the end you've got this COO that the O acts as a bridging oxygen. So bridging oxygens we've seen in silicates, borates as critical in covalent network formation, and they're operative here. When they're operative in a polymer system, that type of polymer is termed a polyester, because the ester linkage is this oxygen with the double bond. So this is polyethylene terephthalate, PET, as you know it. And the other thing that I wanted to point out is that if you look carefully at the structure of these, last day we studied cross-linking, and cross-linking depended upon a covalent bridge between two chains, and in this case it's typically made with sulfur. So we have sulfur attacking residual double bonds in the backbone to form single bonds between backbones. So we have two chains linking. Well, if you look at the features of the polymers that are made by condensation polymerization, you'll notice that in many instances, I think here's a good one to look at, Kevlar, you see the carbonyl group here, the C with the double bond to the oxygen, and on this side you have an amino group, a nitrogen with a hydrogen. And what can happen is adjacent chains can hang the aminos on one side opposite carbonyls from the other side. And look at the situation that we've set up. Here's the oxygen off the carbonyl group, and it's sitting opposite the hydrogen off the amino group. And you know what that can lead to? Hydrogen bonding. And so in many of these condensation polymers, nylons, silicones, hydrogen bonding acts almost as a pseudo cross-linking. It's nowhere near as strong as a true covalent cross-link, but what we do observe is that the nylons, Kevlars, things like this have much, much higher strength, and we're going to learn a little bit later, they have a higher melting point owing to this hydrogen bonding. So I think we want to just document that. Hydrogen bonding operative in nylons and silicones, and this leads to some additional strengthening of the material. What I wanted to do today was to take up this concept that we talked about with regard to ordering versus disordering last day. We talked about low-density polyethylene versus high-density polyethylene. So I want to just revisit influences on ordering. Influences on ordering, and actually what favors crystallization. Factors favoring crystallization. And remember, we're not talking about perfect crystals here. We're talking about local ordering over certain lengths of chain, which give rise to some strengthening of the material. And so I'm just going to go back and revisit 1, 2, and 3 above. I'm going to ask, how does composition, how does tacticity, and how does conformation enhance crystallization? So first thing, let's look at composition. The way to favor crystallization is to make materials more nearly uniform. The higher the degree of uniformity in the polymer, the greater the chances are that it can zigzag back and forth and in a predictable manner set up these zones of crystallinity. So if this is a straight chain or a linear chain polymer, if it's made homogeneous of a same composition, then the chances of its folding back and forth on itself and setting up this local sort of semi-crystalline region are greater than if the polymer has some random variation in composition. So the factor that favors crystallization is having single composition. So homopolymers are much more easily crystallized. So as an example, polyethylene oxide can form a crystalline polymer, whereas if you take the polyethylene oxide block copolymer with, say, polypropylene oxide, the second case is more likely to be amorphous. The second factor we want to look at is tacticity. Tacticity, you know, you've got the three forms of tacticity: isotactic, syndiotactic, and atactic, and the one that's more readily willing to pack is going to be isotactic. So isotactic version will be favored from the standpoint of crystallization, and we have evidence that isotactic polystyrene is highly crystalline. So you see some of these hard polystyrene containers, they're predominantly isotactic, whereas atactic polystyrene is dominantly amorphous. So there's the influence of tacticity. And the third one is conformation. How does conformation act? Well, we've got the linear chains, we've got branch chains, and we've got cross-link chains. And clearly, following this paradigm, the linear chains are favored when it comes to the formation of ordered structures. So if you look at something like high-density polyethylene, that's shown here. This is the opaque milk jug. This has a high degree of linearity in the chains, whereas branching or cross-linking are going to make things very difficult from the perspective of forming crystalline structures. And in fact, here's something that's volume versus temperature. Should remind you of the unit that we've just covered in silicate glasses. We see the cooling curves here at two different rates, and fast cooling has a knee in the curve at a higher glass transition temperature than slow cooling, and similarly with fast cooling there's a higher degree of quenched in free volume. So all of those ideas apply. The other thing I want to look at now is on the basis of what we've seen so far, what are the properties of polymers? Now, we can tailor things to a great extent, but there are certain properties that they all share. So let's document those. First one, electrical insulators. Electrical insulators. Why? Whenever I ask why, we have to look at electronic structure. Here we have strong covalent bonds up and down the backbone, and we have relatively weak van der Waals bonds with some hydrogen bonding in between. In no case are we looking at free electrons. So strong covalent bonds internally. These are intramolecular bonds. No free electrons. With covalent bonds, we have electron sharing, we have octet stability, and the electrical insularity that accompanies that. Second, optically. Optical behavior. While they're transparent to visible light, again, the high strength covalent bonds, transparent to visible light. And in the case of amorphous, when amorphous, they're clear. Amorphous are clear. And when we have the semicrystalline setup, regions of higher atom density, which translate into regions of higher refractive index. And since the refractive indices are not matched between the amorphous and the semicrystalline regime, this acts effectively as an interface that can scatter light. So the semicrystalline, although formally they're transparent to visible light, these in fact prove to be opaque, as you can see from the appearance of that milk jug. Now the question you got to ask is, could you generate semicrystalline zones that were either index matched or on a length scale shorter than that of visible light? We saw that in the inorganic case with the difference between pyroceram glass and visions. The only difference was that the crystallites in visions were much, much smaller, and as a result we were able to get the strengthening effect without incurring the penalty of opacity. Third one is chemically inert. Polymers are chemically inert. Again, the strong covalent bonds, octet stability, same reasons, and this leads to their extensive use in packaging. Packaging, especially of foods and beverages. Foods and beverages exploit this property. And lastly, they're solid at room temperature. Solid at room temperature. The long molecules, even though there are only weak van der Waals bonds operative between molecules. Remember, the strong covalent bonds are within the molecule. If you want to ask the question, is something solid, liquid, or gas, you have to ask, how does one molecule bond to another one of identical composition. And for that, we've got not strong covalent bonds, but we've got weak van der Waals bonds. Weak van der Waals bonds. But they're operating over such large contact areas. These molecules are very, very long, so the long molecule presents a high surface to volume ratio. Very high surface to volume ratio. And that leads to strong bonding, and ultimately it leads to entanglement. So we have entanglement, we have weak van der Waals bonds over high surface to volume ratio, and that leads to solidity at room temperature. And we recognized last day that absent cross-linking, we can reprocess these by reheating. This gives us thermoplastics that can be reprocessed. And even in the case of hydrogen bonding, although the nylons have to go to slightly higher temperatures, we are able to reprocess the nylons. In the case of cross-linking, of course, we have to go to other measures because heating to very, very high temperatures capable of breaking the cross-links will also break the backbone. So these things become not very easily recyclable. And in fact, what I've got here is the recycle codes, which you see on products today. Here's the first one is the polyethylene terephthalate, which we just saw the reaction for, and that's used in these clear plastics for many of the things such as, in this case, it's dishwash detergent, the 2-liter soda bottles, and so on are this. The high-density polyethylene, that's this one here. The next one, V, is the reaction I showed at the beginning of the lecture, polyvinyl chloride. Fourth one is low-density polyethylene, which is the stretch and seal, and so on. And I want you to note that all of these have names associated with them. And these are inventions. All of these materials that I'm showing you are inventions of the modern era. They all came as a result of research, patenting, etc. So you see this one, 1940, 1951. These are very, very recent materials. Polypropylene, 1951. Polystyrene technically was isolated by a German apothecary in 1839 who didn't realize what he had. He had some material that he got out of this resin, and it was around 1922 when Hermann Staudinger reasoned that, in fact, this was a long chain of styrene. It was polystyrene. He wrote extensively on it and eventually won the Nobel Prize for it. But technically, Simon isolated polystyrene in 1839. And then 7 is everything else. So if you see a 7 at the bottom, it's, who knows? All right. So that's the chain of events. So what I'd like to do now is I want to show you a few demonstrations. And in years past, I had someone come in here and do this, but she's since graduated, and there's a whole bunch of other factors involved. So what I want to do is I've got some video footage of the demonstration as it was done. So what you're going to see is several things. The first thing I'm going to show you is the synthesis of nylon. And this is Beaker synthesis of nylon 6,6. It's condensation polymerization. And we're going to use hexamethylene diamine, so that's the base, and a diptic acid, which is obviously an acid. So acid plus base gives water plus, in this case, the neutralized polymer. This is only done for demonstration purposes. In industry, nylon is not synthesized this way. They typically go up to around 300 degrees C. So they're going to take each of these ingredients and they're going to dissolve them in different solvents. So in one case, we're going to dissolve the hexamethylene diamine in an aqueous solution, and then the adiptic acid is going to be dissolved in hexane. Well, hexane is aliphatic, It's nonpolar. It's immiscible with water. So you're going to see two liquid phases, an aqueous phase and an organic phase. So one ingredient is in an aqueous phase, the other ingredient is in the organic phase. The only place they come in contact with one another is at the interface. So you're going to see nylon synthesized at the interface between the two liquids, and here's the reaction. So let's see if this...
So my acid is
This is Heidi Birch speaking.
dissolved in water, which has a higher density than hexane. And then I have my acid dissolved in the hexane. So what's going to happen when I pour that in? It's not going to mix, right? What's going to happen? It's going to phase separate, exactly, and we're going to have strata. Is that going to help or hurt our reaction? It's going to hurt our reaction, right? Because to have a good reaction, you need intimate mixing. Well,
this is like the ouzo water problem.
Oh, shut up.
so this is actually pretty unexciting. Nothing really interesting has happened. It's just kind of sitting there. Nothing's exploding out of the beaker. Nothing's coming out. It's
Train your eye right here.
kind of tame. But if you look carefully, you can kind of see, where's my pointer? Kind of see this film right there. See that big bubble? Well, there's a scum that's floating at the interface between the two layers. That's actually the nylon that we formed. What happens is, I mentioned that nylon has that excellent chemical resistance. Well, when we formed it, it made a barrier film between the two layers so that no more reactants could get through to each other to form more nylon. So what I have to do is remove that barrier film to allow the reactants to come into contact. And I'm doing that by drawing off the nylon as it's formed. Because I'm drawing off the film, or very
I'm going to show you, we had a close-up of a previous year when she did it. We actually had a camera focused right on the beaker. So you get a better scene of the formation of the nylon. It's happening right here at the interface between the hexane and the aqueous solution. So the nylon is forming right here. And as soon as the nylon forms, it seals off the reaction. So no more reactants can get here. What she does is she pulls this up, and as she pulls the nylon up, she exposes fresh interface. So that everything's occurring at this interface. It's a self-limiting reaction. So this next one, I think, shows it's just a little bit better.
hazard. And what's happening is the polymer I'm forming has a very broad molecular weight distribution. It's not all 240 grams per mole or whatever. And that greatly affects the mechanical properties, and in fact, it affects them detrimentally. So the mechanical properties of this nylon that I'm forming aren't very good.
Okay, the second one I'm going to show you is a demonstration of the role that the glass transition temperature plays in rubbers. Rubbers are materials that are cross-linked, and they gain their bounce from the fact that if you pull on the rubber, these cross links will cause you to have to recoil. But if you cool the rubber below the glass transition temperature, the entire structure becomes a rigid solid. And so the rubber loses its bounce. If we, in our lab, if we have to make, for example, a hole through a rubber stopper, if you take that rubber stopper, put it on a drill press and try to drill, it's very dangerous to do because the rubber will grip onto the drill bit. If you quench the rubber in liquid nitrogen, take it below its glass transition temperature, the rubber behaves as a brittle solid, and then you just drill right through, get a nice clean hole, and then the material heats back up above its glass transition temperature. So Heidi's going to show you two different rubbers, one that has a glass transition temperature above room temperature. So room temperature is already down here, and the rubber ball, I'm saying in quotation marks, the ball is going to act like a billiard ball. It's solid, very poor bounce. The other one has a glass transition temperature negative degrees C, and so at room temperature it bounces well. So she's going to, in one case, heat both of them above the glass transition temperature, put them in boiling water. In the other case, she's going to put them in liquid nitrogen. So she'll turn both of them into solids and both of them into the liquids.
Okay, the thing I want to talk about now is the effect of temperature on polymer molecules. Basically, when do I get rubbery behavior and when do I get glassy behavior? Because I can get the same polymer to exhibit rubbery behavior or glassy behavior depending on the temperature at which I use that material. As Dr. Sadoway told you, polymers have what's called a glass transition temperature. The type of behavior that I get is determined by my use temperature relative to my glass transition temperature. So I have here 6 little balls with faces painted on. The ones with the happy faces are polyisoprene. The ones with the sad faces are polynorbornene. Now, polynorbornene is a synthetic rubber that was developed during World War II when we didn't have access to all the rubber trees grows in Southeast Asia. So the happy balls are happy because their glass transition temperature is -67. So our use temperature at room temperature is much greater than their glass transition temperature, so they behave as a rubber would. The polynorbornene has a glass transition temperature of 40. So we're actually below its glass transition temperature at room temperature, and it just dissipates all the energy. We get a much more glassy-like behavior from this material, and it doesn't bounce. So what we can do here to demonstrate the effect is we're going to raise the use temperature of both materials, and we're going to lower the use temperature of both materials. So I'm going to drop them in boiling water and hope that the little faces stay on, because I just painted them on with white out. I don't know how that's going to work. And then I'm going to drop 2 of them in liquid nitrogen. Now these will be our controls. Remember, polynorbornene, polyisoprene. Now something to think about, which I know Dr. Sadoway always likes to ask, is why does one have a high glass transition temperature and why does one have a low glass transition temperature? And I'll leave you to ponder that little conundrum while I try to fish these bad boys out. Okay, oh, why not work? So this is the polyisoprene. Can you hear the sound that it makes? When I drop the one that's at room temperature, I get a nice rubbery sound. And I'll chase it later. When I drop that one, I get a plastic, hard, glassy sound. I've cooled it below its...
Did you see that?
And now it has a totally glassy impact, like if I were knocking 2 balls together.
Pay attention.
Now let's go into the polynorbornene. Oh, his eye came off. Same thing. I've cooled the polynorbornene below its glass transition temperature as well, so it too exhibits a glassy collision, like a pool ball. Now, in here, now this is the polynorbornene, so it should still continue to bounce because we've raised its use temperature above its glass transition temperature, further above its glass transition temperature. That's not the exciting one. The exciting one is, if I can get it out, what happens to the polynorbornene? This is the sad ball, the one that wouldn't bounce at room temperature. By raising its use temperature above its glass transition temperature by dunking it in boiling water, I get a rubbery response. So the take-home message of this is, whether you get a plastic or whether you get a glass depends on the use temperature relative to the glass transition water.
Okay, the last thing I'm going to show you is something very peculiar with macromolecules. I'm going to show you 2 beakers that contain liquids that are clear colorless, but they've been, in this case, green food coloring has been added. The first one is water. And when the propeller spins, you get a vortex. In the case of polymers, at low spin rates, the same thing happens. At a low spin rate, you'll get a vortex. At a high spin rate, when the spin rate goes faster than and these are liquids. We're above glass transition temperature. But if you try to spin too quickly, you get shear dependent behavior. It's peculiar with long chain molecules. And what happens is, at very, very high shear rates, the molecules actually won't slip fast enough, and they essentially behave as an elastomer. So at very high shear rates, instead of seeing the vortex trough, you see quite the opposite. And this is called the Weissenberg effect, and it has to do with the inability of the molecules to move quickly enough over one another. Let's see what this one looks like. This is a short one.
When I turn it on, as you can see, I get a tornado or vortex effect. Now,
That's water.
Now, that was just plain water with a little secret food coloring recipe in it. Now, this is something a little bit different. This is a solution, a 1% solution of polyethylene oxide in water. You can see the chemical repeat unit of polyethylene oxide up there. Now, when I turn this on, something else happens entirely. It climbs up the stirring rod, and the winging off you see is, I've overcome the centrifugal force and it's being flung out.
So there's the Weissenberg effect, and this is at very, very high shear rates. So the one thing I wish she'd done is turn the speed down. At very, very low speeds, you'd actually see the vortex form because you're asking the molecules to shear over one another at a slow enough rate that they can keep pace. So this is very different from Newtonian fluids. This is non-Newtonian flow. And this you have to understand if you're doing such things as injection molding of polymers. Because they do weird things at very, very high shear rates. And let's face it, if you're in the business to make money, you're not going to be gently plunging the piston into the mold. You want to pop these things out quickly. So there's a lot of esoteric physics involved. Okay, I'm going to hold that there. What I want to talk about now for the last few minutes is the cultural impact of the advent of polymers. In fact, many of these come under the general rubric of synthetics. These are man-made materials. These are synthetics. And they all occurred, the real burst occurred at the dawn of the 20th century. And what I like to talk about is the pattern of adoption. And this is something that occurs with other materials, but certainly in the case of polymers. At first, it's wonder. They have these strange properties that we've seen some of here. And then people go crazy with substitution. And what we find is that, for example, the first commercial polymer was Bakelite, and Bakelite was used for such things as billiard balls, piano keys, and so on. So you have what I call the fake everything. So you have faux ivory, which then means you can have ivory-free billiard balls, ivory-free piano keys, and so on. You can have, with the advent of nylon, you have fake silk. And so you have, instead of using silk stockings were a luxury afforded only by the rich. With the advent of nylon stockings, there's a democratization. Price plummets. Huge social changes take place. So all sorts of things take precedence that previously couldn't happen. I think I've got some shots here. This is an ad from something like a Look magazine. This is Bakelite, and if you go to Grandma's house, you may even see some of these large coffee urns, and these handles on the side, they're sort of brownish. These are made of Bakelite, and it's a phenolic resin that's made by carbolic acid with formaldehyde. So it's an addition, a condensation polymerization. And note the symbol here for Bakelite. Bakelite, there's a B with an infinity sign underneath it. The material of 1,000 uses. And these are all substitute parts that previously were made of metal or wood, now being made of Bakelite. By now, I mean 1910, 1915. So big change. And plus, you know, certain parts that used to be made of metal are now being made of Bakelite, which is an electrical insulator. And for electrical applications, in certain instances, you do not want the ability of that part to conduct electricity. So that's the sort of thing that takes place. And then we have new uses, new products, new devices. And then here's a shot from Fortune magazine, 1940. I'm referring to them as plastics, and I'll explain why in a second. But all these new products, you've got the telephone here, fashion, auto parts, footwear, all of these different things. There's LP record. You don't know what this is, but years ago there was an electromechanical device called a tone arm with a needle in it, and it used to play records. Yeah, well, they were made of vinyl. Actually, they're made of polyvinyl chloride. look at this thing here. You see this thing? That's a film strip. You know, photography had been invented back in the early 1800s. The mere fact that you can go to the movies is a result of the advent of macromolecular chemistry. Without celluloid, there's no way you could take glass plates and move them at 24 frames a second and watch Star Wars. You just can't do that. All right? You have to have the ability to put halide on something that is flexible and can be made in long strips. And there was no material until the advent of polymers. Why plastic? The general public refers to these as plastics. If I go to Shaw's and I'm checking out and they ask me if I want paper or they ask me what kind of bag I want, sometimes I slip and I say the polymer bag, and they look at me and that one. You know, they just... so it comes from the Greek word meaning to shape, and it's a cognate of the word potter. So plasticos really means something that can be shaped, and many of these products are made by processes that involve starting with polymer that the shape is changed. And that's what makes it so easy to stamp things out. All right? This is also from the 1940 Fortune magazine. This is a whole new world. I don't know if you can read this definition, but here's an area called cellulose. There's nylon island over here. There's cast phenolic. I mean, the whole world. There's the acrylic mountains. Everything is polymer. Everything is polymer. All right? I recall seeing in an antique shop a ladies' Waltham watch made here in Waltham, Massachusetts in 1922. Platinum case encrusted with diamonds. The crystal was made of acrylic. Acrylic has very poor scratch resistance, but acrylic was an advanced material. And by golly, they were going to make it out of acrylic. It's an advanced material. And it keeps going and going. Here we are after World War II. This is plastics. The future has arrived. At first, it doesn't look like anything. It looks like abstract art. Actually, this is a room. This is an entire room made of sprayed polyurethane foam. This is 1968. People going crazy over polymers. Right? But then people come to their senses, and this book here documents quite nicely the next stage, which is the chagrin. And for that, I want to take you to a piece of iconic filmmaking when people are starting to wonder what's the real future of polymers. This could be you 3 years from now. He's just graduated from college and he's coming home. That's a young Dustin Hoffman in 1968. Okay, now this is the scene. Watch. That's Angela Lansbury.
Oh, I think it's your future. You're lying.
Well, that's a little bit hard to say. Ben. Excuse me. Mr. McGuire. Ben. Mr. McGuire. Come in a minute. I'll talk to you. Excuse me, John. Thanks. Thank you. I just want to say one word to you. Just one word. Yes, sir. Are you listening? Yes, sir. Plastics. Exactly how you remove. There's a great future in plastics. Think about it. What do you think about it? Yes, sir. I'm said. That's a deal.
Well, in point of fact, that's so ironic. By 1968, it's not true to say that there was such a great future in plastics, because people started to realize the next thing about, which is the concern. And what's the concern? Well, I've already talked about recycling, but there are other concerns, and they all come from this: environmental safety and health. We know about the environmental, the difficulty to recycle. And that's a challenging problem to this day when it comes to thermosets. And, you know, even the ones that are recycled, there's this concept, recycle as opposed to reuse. We recycle polyethylene terephthalate, but I hope you don't think that this goes back on the supermarket shelves in about 20 days as another bottle containing dishwash detergent. There's a cascade of utility. Cascade of utility. So you start off with something of high value, then it gets shredded, maybe end up as carpet fiber, then you end up as something that could get molded into a park bench, but the value keeps going lower and lower and lower. So this is still a thorny issue when it comes to much of polymers. And then, of course, they're not degradable, non-degradable in landfill. Right? Why? Bonding, strong covalent bonds. Very difficult. And then the second one, so that's the E. And let's talk about the H, health. We saw the Weissenberg effect. In order to facilitate the processing of polymers, we add lubricants, what's effectively a lubricant, to enable the polymer, the long chain molecules, to more easily slip over one another. And these additives are called plasticizers. Plasticizers. So they facilitate slip. And these are low molecular weight organics. Low molecular weight organics. So if they're low molecular weight and they're organic, they have vapor pressure, they have a very, very low melting point, low boiling point. So they're volatile. And when you're finished processing, you like to get most of them out, but they're embedded inside macromolecular solids, and they take time. The new car smell that you smell, that's plasticizer, and you'll smell it until the last of the plasticizer is out. And the trouble with some of these plasticizers is that they have structures that are similar to certain hormones. And so they can be ingested, and over certain periods of time could, I underline could, it's very difficult to prove direct cause and effect, but they're becoming increasingly suspect in genetic disorders. So that down the road, 25 years down the road, you might find that people that have been exposed to these could be the bearers of more tumors than the general population. One commonly used one is dioctyl phthalate. This is one of the most commonly used lubricants. And, you know, I talked about the democratization, the faux silk giving rise to nylon stockings for everybody. But, you know, those early pictures of polymers as these wonder materials, by the time that movie was made, the people were starting to use the term plastic to be synonymous with cheap, with shoddy, with junk. Plastic didn't have the connotation it had when the watch with the acrylic crystal was made. Things had changed a lot. And part of it has to do with this recyclability. Look at this. This is the annual production of polymers, about 100 billion pounds, 50 million tons, and only about 3 to 4 million tons recycled. And by recycle, I mean returned. You might ask me, well, why is it that if you can't reuse this directly, do they make it recyclable? And the answer is, if this were not recyclable, and the aluminum can is recyclable, people would not buy aluminum cans bearing soda. They would buy only polymer because they wouldn't want to pay the 5-cent deposit. This is human nature. So if once we decide to recycle any beverage container, we must demand a 5-cent or whatever the deposit is across the board. Otherwise, people will base their purchases on the one that is least environmentally friendly because it doesn't have the deposit on it. That's a policy issue for you. 3 to 4 million tons recycled. Steel, the U.S. annual production is 140 million tons, about 3 times that. 80 million tons is virgin metal, and about 60 million tons recycled scrap. A lot of recycling. Steel is the most recycled material, by far. You might say, well, what about aluminum? I heard aluminum was, yeah, you heard it from the aluminum industry. There's 4 million tons of aluminum capacity in the United States, about 1 million tons recycled, and most of it is thanks to the used beverage containers. But this is a very special situation because this is made of 3 different alloys that were designed for the environment, DFE, designed for the environment. They were chosen, the constituents of those alloys were chosen to allow for recycling. So they contain only aluminum, silicon, and magnesium. And these will melt down and allow to be reprocessed very, very easily. But you know, I like to give the example. I could take the door off a 1928 Model T Ford, throw it into an electric arc furnace, melt it down, reshape it, and put it on a 2005 T-Bird. The same steel. Okay? I cannot take the wing off McDonnell Douglas DC-3 aircraft, it's aluminum, melt it down, and put it on tomorrow's Boeing 777 because the different alloys are used in the top of the wing and the bottom of the wing. One set contains copper aluminum, the other set contains zinc aluminum, and when you co-melt that, you end up with a mix that's neither fish nor fowl, and aluminum's reactivity is so great that to separate the copper and the zinc is either impossible or too costly. So too costly is equivalent to impossible. Okay? So what's the conclusion? You end up with virgin metal. So I think this is a good place to stay with these wonderful materials, and I'll see you on Wednesday.